Hi everyone and welcome back to PrepFusion. So today we will start the lecture 12A of linear algebra chapter. This is the last topic basically here we will study about the vector space, vector subspace, linear span, then basis of a vector, okay, and few more other things about vectors only. So this is the part A, and in the part B we will do the other remaining topics. So yeah, let's start. So in the previous lecture we learned a lot of things like eigenvectors and eigenvalues. We finished the eigenvectors and eigenvalues. I hope you have got a practical approach to what does eigenvectors and eigenvalues mean. I have given you all the definitions, all the different definitions of eigenvectors and eigenvalues. Okay, this will also help you in the upcoming subjects like signal system, control systems, if you haven't studied yet. Okay, so yeah, let's start this lecture. So first of all, let's understand what does vector is. So I have already explained you a brief about vectors like in physics, right? Like in the previous lectures I've told you, like, just for now understand vector is a column matrix, just for now understand vector is a row matrix. Okay, I have given you like the what do you say 2D vector diagram, right, in physics, I cap and j cap, all those things. So let's understand it first. So vectors in physics is a geometric entity that has both magnitude and direction. So we have been studying this from class 11th, that vector has two things defined vector. One is the, like, let's say I have a vector v, right? One will be the magnitude of vector v and another one will be the direction of the vector v, a v cap. Okay, this is wait a second, this is a v cap, right? So one is the magnitude and one is the direction of the vector. Okay, then vectors in linear algebra is a matrix which has either only one row or only one column. Okay, so in linear algebra vectors have only one row or one column. We have been already discussing about this previously. A matrix having only one row is called a row vector. So if a matrix has only one row, it is called row vector, that we all know, just revising few things. And a matrix having one column is called column vector. Row matrix and column matrix are called vectors. Okay, so this is the basic definition in linear algebra. So here vectors in linear algebra is a matrix. Okay, so in linear algebra what do you have? We have ordered things, right? Like things or ordered things. So vectors in linear algebra, like here we have array of numbers or anything, right? So I can write ordered numbers. Now these numbers mean something. Okay, if in a column matrix, it is written 1 2 3. Okay, 1 2 3, then this is order, right? This is ordered. 1 is coming first, then 2 is coming second, then 3 is coming third. So 1 means 1 in the x direction, 1 unit in the x direction, 2 unit in the y direction, and 3 units in the z direction. Okay, that's why they are known as ordered numbers, right? Ordered numbers. So let's see few examples of vectors. So I have one vector v naught which is equals to I plus 2j cap. So how can I write this in the matrix format? Why is this important? Why is this important? Because mainly in computers we can't obviously store vectors, right? We can't store vectors, that is a physical quantity. What do you store is, we store matrices. Okay, we store matrices, and matrices are basically telling us about vectors. This vectors has other use cases also, but this is also one of the use case vectors. Okay, so that's why how to represent in the matrix format. So here this is VO I cap plus 2 j cap. This is in the physics format, right? Normal whatever we used to write in the physics topic. So now if I want to write this in the matrix format, either I can write it in the column or row. Like we know we can write anything, right? Column or row, we just have to take the transpose. I've already said to you this in the first few lectures. So this is what is the order of this. This is 2 cross 1, right? 2 cross 1. Then I can also write this in the row format, row matrix format. So this will be 1 cross 2, 1 cross 2. Okay, so here what do you observe? This is a ordered pair, right? Ordered. So 1 comes first, then 2. So this is a ordered pair. Here we can see that ordered pair. Okay, now how will I define this one? So this is in 3 dimensions. Here I had 2, right? I will need 3 cross 1 column matrix. So this time my v1 1 2 3, and obviously I can write this in the row format as well. 1 2 3. Okay, so as you can see, again this is in the ordered format. Now this is called a ordered pair, right? Ordered pair. This will be called what? This will be called a ordered triplet. This will be called a ordered triplet because we have 3 numbers. Okay, now here I have 4 numbers, right? So my matrix, let's do it a bit quickly. v2 will be 1 2 3 4. Also I can write 1 2 3 4. So this is called a ordered quad. Okay, so I'm just taking few examples to make you comfortable with this concept of vectors. So we will go very slow in this because many students get confused with this. This is called a ordered quad. Okay, so these are basically whatever we can represent vectors in the matrix format. So let's say now we have n number of vectors, right? N number of vectors. This will be again called a, now instead of this quad, triplet, pair, right? We can't every time call different numbers. We call it tuple. We called it tuple. So tuple is another format which we used to represent where these numbers won't change. These numbers won't change. That is why it is called a tuple. So this v3 can be represented in the column format. Sorry, v3 1 2 3 4 5. Okay, now this is 5 cross 1, and this will be called a ordered. Now this will be called, instead of like quad, I can name everything different, right? So what will call this? I will call this ordered 5 tuple. So elements are 5 and it will be tuple. Okay, as they are not changeable. So I can write this in column format also, same thing only. Okay, vectors can be represented in both column and row format. Slowly I am making you comfortable with the terminologies, then we'll go to much deeper concepts. Okay, so yeah, this was the vectors. Now this was one vector. Now what is set of vectors? So vector here, right? These are representing directions. I hope you understand. Or these can represent other things also, like 1 apple, 2 mangoes, 3 bananas. This also can represent. That's why we want to put data in the computer. How do you put data in the computer? Like this also you can represent, right? So yeah, I'm just giving you one example. So what are set of vectors? So set of vectors, anything wherever set is written, right? Anything wherever set is written, that means it is talking about similar items. Similar items. Okay, so set means similar item. So set of vectors means set of similar vectors. So X is a set of this many m vectors. So set of m vectors of n dimension each. So X has n dimensions and we have m vectors total, like each vector has n dimensions and we have total m vectors. So how can I write our X vectors here? So we're just getting comfortable with the terminologies. So my X1 I can represent like a column matrix, okay, where its first element will be something like what I can write, x11, then x22, okay, x21, x31, right? Or I can write like this. This will be something like this: 11, x12, x13, and it goes all the way down to x1 n, because it has n dimensions. So its order will be n cross 1. It will have n elements in the those. So its order will be n cross 1. Okay, now what is like x2 can also be written like this. So x2 can also be written like this. Just hold on a second. So this will be 2, right? This will be 2. Okay, and this will go on till m. So this will be x x m1, then this will go on till x mn. Okay, so yeah, this is the case. Basically this is how you represent the set of vectors. Now let's do few examples and from there we'll understand. So which of the following are valid set of vectors here? So which of the following are valid? So I told you, right, set means similar items. So here what I have three vectors, three column matrices means 3 vectors, and each of them has dimensions 2. So this is a set of vector. There is no issue with this because this is satisfying the definition. Set of n vectors of n dimension, similar items. Here what is happening? I have 3 vectors, but 2 of them have dimension 2 and 1 of them has dimension 3. So will it be a set of vectors? No, right? It won't be a set of vectors. Okay, so because the dimension of this is 3, so this is 3 dimension. Okay, that was about the set of vectors. Now let's understand set of linearly independent vectors. What are linearly independent vectors? A set of vectors is, okay, I think it shouldn't be is, it should be r. Linearly independent. A set of vectors are linearly independent if no vector can be expressed as a linear combination of the other. Okay, as no vector can be expressed as a linear combination of the other, so then only they are linearly independent. If they are linearly dependent, that means one vector can be represented in terms of the other. What do you mean by this? So here I have 2 vectors a and b. Okay, can I represent this a vector in terms of this b vector? Can I do this by just simple scalar relationship, right? Scalar linear combination means scalar. So I can only move along this line. If I want to scale this b, right, I can only move along this line. So these b and a are always linearly independent, right? This b and a are always linearly independent. Okay, it all depends with what vector you are trying to scale. Okay, with what vector you are trying to scale. Now here, can I have 2 vectors c and a. Can I represent this b? It may, because I don't know. I have like three dimension, right? I'm not able to tell, but this is the basic thing. With the help of this a, can I represent this b vector? Or with the help of this a and c, can I represent this b vector? Or this c and b, can I represent this a vector? Or a and b, I can represent this c vector. Mutually, basically it is about the mutual relationship, right? So this is about the linearly independent. So here, how to prove it basically? So I told you a set of vectors are linearly independent if no vector can be expressed in a linear combination. So when they are linearly dependent, when they're not linearly independent, that means they are linearly dependent. So if a comma b vector comma c vector are linearly dependent, not independent, linearly dependent. Okay, that means that c will be equals to k1a, c will be equals to k1a. Like it is a scalar, it can be written as a addition of a and b, okay, with a scalar multiple, basically k1a k2b. Okay, so if they are linearly dependent, then I can write C in terms of these two vectors. It's same as the rank concept, same as the matrix concept, linearly independent rows, dependent rows. We have been already doing this. I'm just rewriting things over here. We have been already doing this since like lecture 1 and 2. Okay, so we have been doing the same thing. If you observe the linear algebra chapter, we are just talking about the linear dependency. That's why the name is linear and algebra. This is also algebra, right? So everywhere we are using the same concept, just in a different way. Okay, so here I can rewrite this equation like this: C minus k1a minus k2b equals to 0. Okay, so what I can do, like the standard way to write a linear dependent, three set of linear dependent vectors is something different. That's why I'm going to that format only. So I can divide by k1 k2 on both sides, k1 k2 k1, where k1 k2 is not equals to 0, right? K1 k2 is not equal to 0, very important. Okay, I forgot the C over here. This is C. So what I can write is basically I can write lambda 1 plus a plus lambda 2 plus b vector. Lambda 1, lambda 2 are just these constant, right? These are scalar constant. So I can replace them with lambda 1, lambda 2 and lambda 3. Lambda 3 c equals to 0. So this is the main relationship for three vectors to be linearly dependent with each other. If I now here, basically what is the important point? What is the important point? The important point is lambda 1, lambda 2, lambda 3 can't be all 0 simultaneously. All 0 at once. Okay, so basically lambda 1, so this is the relationship. If three vectors a b c are linearly dependent, they can be written in this format, where lambda 1, lambda 2, lambda 3 are scalar multiples and they can't be all 0 at once. Okay, they have to be, at least one of them has to be non-zero. Okay, then only we can satisfy this equation, because if all of them are 0, anyways we are getting 0 equal to 0, that is anyways true. Okay, that's why. So yeah, let's do another example problem over here. It is asking us that what will be the relation between a b c and d if a b c d are set of linearly dependent vectors. If a b c d are set of linearly dependent vectors, then what will be the relationship between A, B and C, D? Okay, again we are coming back to the relationship thing. Okay, so basically what we can say, like we have just learned this, right? If three vectors are linearly dependent, that means it can be written in this format. So if four vectors are linearly dependent, it can be written in this format. So it can be written lambda 1 A plus lambda 2. Basically they are collinear. They are collinear. If you remember during your class 10 days, how you used to find dependent vectors. You used to again do that determinant thing only, if you recall. Lambda 2 B plus lambda 3 C plus lambda 4 D, okay, equals to 0. So this is my a relationship between the vectors. Let me change the color to this. And what is the important condition over here? The important condition is all of them can't be equal to 0. Lambda 1, lambda 2, lambda 3, lambda 4 can't be equals to 0. Lambda 1, lambda 2, lambda 3, lambda 4 can't be equal to 0. Okay, sorry, can't be 0 simultaneously. All at least one of them is non-zero. At least one of them is non-zero. Okay, at least one of them is non-zero. Okay, so they can't all be 0 simultaneously. So now here this is talking, right? If lambda 1, lambda 2, lambda 3 are equal to 0, then this also and this condition has to be also satisfied. Then if x is a set of vectors, then they are set of linearly dependent vectors if this condition is satisfying. Okay, so this is what this means, like they are all not equal to 0 simultaneously. At least one of them has to be 0. This is talking about the magnitude of all of this, right? So yeah, then x will be a set of linearly dependent vectors. That is what we did with examples. If we are not able to satisfy this equation, right? We're not able to satisfy this equation, then they will be set of linearly independent vectors. So I should write they are set of linearly independent vectors. Then x is equals to x1, x2, x3 will be a set of linearly independent vectors. This is already written over here again. Okay, I should write like this. I've already written the second point, so I don't need to repeat this. So x will be a set of linearly independent vectors. So again, the next key point, what is the next key point? Next key point is x1 is equal to x11, x12, x23. So here I have been given three vectors, right? Now x1, x2, x3 will be linearly dependent, or first of all, obviously order of them have to be same. Okay, the order have to be same, else like they are not even a set, right? They are not even a set, so their order have to be same. Then there must exist three scalars, at least one non-zero, such that we can write in terms of this. We have already known this condition. So and now I'm writing in terms of the vectors. Let's solve this actually. Until now what I've been doing, I've done in terms of not matrix, not just simple physics, right? Now let's solve actually one of the questions, and from there we'll understand. So we have a x which has three vectors, which is set of three vectors, such that each vector has three dimensions. Okay, each vector has three dimensions. Now the three vectors satisfy the following equations: lambda x1, lambda x2, lambda x3, and where this is, okay, I should write this not equal to 0, not equal to 0. Just hold on a second. Let a equals to x1, x2, x3. So a is a matrix over here. So I should at least say a is a matrix, right? A is a 3 cross 3 matrix. If you can understand, like we're just arranging the columns, right? We have been doing this like augmented matrix. How have we been arranging? We're just arranging the columns, right? So here also this we're arranging the columns. So this has become a 3 cross 3 matrix. Okay, so this has become a 3 cross 3 matrix, and this is x1, x2, and x3. Okay, so now we have to tell which of the following options is or are true. All rows of A 3 cross 3 are linearly independent. Okay, let's talk about this. So we have been arranging this in columns, and it is talking that the columns are linearly dependent. Why? Because this is satisfying this equation. If this is satisfying this equation, that means this is satisfying this equation. That means my x1, x3, x3, x1, x2, x3 will be linearly dependent. Now, if they are linearly independent, linearly dependent, that means the determinant will be 0. The determinant will be 0. The rank will be less than 3. Okay, that's for sure. Rank will be less than 3. Now, it is talking about the rows. There it was talking about the columns. It doesn't matter. For a 3 square matrix, doesn't matter. Obviously, we know that the number of linearly dependent rows and number of linearly dependent columns will be same only. Okay, so it is talking about the all rows are linearly independent, which is wrong. There are at least one row which are linearly dependent. So this option is gone. Now determinant of A is 0. I already said you to this that yeah, determinant of A will be 0 because there are linearly dependent columns due to this relationship. Okay, so determinant of A will be 0. This is correct option. Next, X is a set of linearly dependent vectors. Yes, this is true. X is a set of linearly dependent vectors because it is satisfying this condition. Right? It is satisfying this condition. Hence, it will be a set of linearly dependent vectors. I hope you are understanding, right? This dependency we have been doing since the starting itself. Like not in this lecture, since the past few lectures. We already know. Just applying the same concept with just a different nomenclature. Just the naming is different. Concept is same only. We're just talking about the dependency about the rows and columns. Okay, just they are represented in a different manner here. Okay, next, rank of A is less than equals to 2. Is this true? This is true, right? Because rank of A can't be equals to 3. Okay, but it can be equals to 2. Why can't it be equals to 3? Because the determinant is equals to 0. Obviously, it is not a full rank matrix because there are dependency between the rows or columns. So it has to be less than 2. But what? I don't know because I have to know the vectors as well. From there I can directly calculate the rank. Okay, exact values of the elements of the vectors. Okay, so I hope you got this example. This is a very good example, and this cleared about the linear dependency and independency of vectors. Now let's like this was just an example. Now what will be the steps to find the dependency without even doing the methods how to find the linear dependency? I hope you got the point how to find the linear dependency, right? But let's I have written it down in the step by step format how to find the linear dependency or independency between a set of vectors. First, you have to arrange the set of vectors, row vector or column vector, in a matrix, as we already did over here. It arranged the row vectors, column vectors in a matrix. Then calculate the rank of the matrix. Okay, so the rank, if rank of A is equal to the number of vectors, number of vectors. Okay, rank of A is equal to number of vectors. That means obviously there is no dependency between the rows and columns. That means it is a set of linearly independent vectors. All the vectors are linearly independent. Now, if the rank of A, that whatever matrix we created, right, is less than the number of vectors, if the rank of A is less than the number of vectors, then it will be a set of linearly dependent vectors. It will be a set of linearly dependent vectors, not independent vectors. Okay. So like only these two things we have to do. So let's do one example, and from there we'll understand again, right? So this is a question. You can pause the video and solve for it. Calculate the value of alpha where alpha is greater than 0 such that the vectors are linearly dependent. So it has already told that vector will be linearly dependent. If the vectors are linearly dependent, that means the columns will have some dependencies with them. That means the determinant has to be equal to 0. If I form a matrix with these 3 columns, so I will form 3 cross 3 matrices. Basically, now if I had 4 vectors, right? If I have 4 vectors, now I will form a 4 cross 3 matrix. 3 cross 4 matrix, and anyways the rank will be less than the number of vectors. Rank will be less than the number of vectors. Why? Because at max the rank can be 3 over there. Okay, minimum of number of rows or number of columns. At max the rank can be 3. Obviously rank is less than number of vectors. So anyways that will always be linearly dependent. Okay, if my dimension of each vector is less than the number of vectors. Okay, I will write this point later on. Let me write here also. So okay, I should not write dimension because with dimension you will get confused. I should write this one, right? Whatever nomenclature was used over here, because we'll learn about dimensions later on. Okay, it has already dimensions over here. We will learn about dimension, don't wait. For now, just understand the dimension is basically the order of this matrix, right? order of this matrix. Uh, if dimensions of each vector is less than the number of vectors, then I should write this in another page actually. This one is also fine. I should write this as key points. Then basically my rank of A will always be less than number of vectors, right? Rank of A will always be less than number of vectors, because obviously rank of A is the minimum of the order, right? Minimum of the order. So it will be set of always set of linearly dependent vectors. Okay, so now you have to calculate this, right? You try to calculate. So we will obviously form a matrix over here. If you form a matrix over here, so this will be 2 minus 3 alpha and 5. This will be, okay, where did I go? Oh, no, 3 1 2 alpha 1 2 3. Okay, so here you have to make the rank less than 3. So easy way out is find the determinant, okay, and from there you can easily make the rank lower than 3. So what you can do, we can simply, you have to make determinant of a0, right, equal to 0. So if you want to make determinant of a0, then what's the determinant of this is, I'll do few operations. This is 1, right? So what I will do is 3 alpha minus 4, this is 2 times, so minus 5 this will be, and this will be 3 times subtract, so this will be minus 1, and this will be 2 alpha 2 alpha minus 9, this is 0, this is 0. So this is 1 times minus 0 equal to 2 alpha minus 9 minus 5 equals to 0. Okay, so let's equate these equations. This will, if I take the minus as common, right, if I take the minus as common, minus will go out, so this will be 6 alpha square. What I am trying to say is, if I take the minus common over, everything will become plus, right? This will be plus, this will be plus, this will be plus. 6 alpha square minus 27 alpha plus 8 alpha minus 36 plus 5 equal to 0. Now this will be 6 alpha square minus 19 alpha minus 31 equal to 0. So I can divide alpha square minus equal to 0, right? So basically I've already solved this down, so you will get choose two solutions, and we'll take only alpha equals to 4.3 this is 3, right? 35. Okay, so another one will get as negative solution, okay, and we'll reject that, and alpha will be equals to 4.35. Let me just quickly check again if I'm correct or not. Just hold on a second. Minus 1.18. Yeah, I'm correct only. So it will be 4.35. Another one will be negative, and we will ignore that solution basically. Okay, so let's study about vector spaces now. So what are vector spaces? Basically, vector spaces are set of vectors itself. They are also set of vectors having common property are called vector spaces. So basically, it is a set of column vectors which have some common property. What are those common properties? We'll talk about those, right? So set of column vectors, right, that has some common property with it. What are the common properties? So basically it has to have the same dimensions over here. So basically if you see, let's take one example. Slowly with examples we'll understand this. So let's say this v belongs to this r raised to power 1. So what does this r means? R means all the elements inside this vector will be real. So here, and 1 means it is one dimension vector, only one elements. Okay, each, like there may be many vectors, right? 1 2 3, there may be five vectors, but all of them have the same dimension, that is one dimension. That's why this is like written like this, r raised to power 1. So x, like this is x, which x belongs to real, so all the elements inside this vectors will be real. Okay, that is what this v means. Now here I've written one example, like v is a vector space. V is a vector space which belongs to all, like which has all real numbers and dimension is 1, hence it can be written like this, 2 0 minus 1, 2 0 minus 1. Okay, and like in this, right, in the number line, what does this represent? Visually, what does this represent? Visually, this represents like this. So here this is a number line, right? This is a number line, so this only represents one dimension, that's why I have only one line. So I will cover this r raised to power 1 covers all of this whole line, right, from minus infinity to plus infinity, all the real numbers, all the real number line. So in this case we are only taking three vectors here, 2 0 and minus 1. So 2 is here on the right hand side, then 0 is here, and minus 1 is on the left hand side. Okay, 2 0 and minus 1. So I have three vectors over here. So this is a vector space here, this is a vector space over here, right? So this is how you denote this. So basically let's learn about the standard notation. These are few standard vector spaces. So these are few standard vector spaces. I should write here standard vector space. Okay, so what is the notation over here? The notation is basically v belongs to this vector space r raised to power n, which has dimension, like this n represents the dimension, and this r represents that it is it has all real elements inside it. So let's take another example, right? So it is v belongs to r square. So v is a vector space, okay, which has two dimensions, and it has all real elements. So here x1 y1 x2 y2, okay, it is two dimension, that way it has two elements inside a vector. So it is a set of vectors, set of multiple vectors, and all of them has two dimensions, and all the elements inside this is all real. Okay, so xy belong to all real. Then if v, it can also be written like this, v is a collection of vectors x1 x2 and all of them, x belongs to r. These are each vectors, right? These are each vectors. Okay, and this represents, if I want to represent this, this can be represented like this, x1 y1 then x2 y2. Okay, this can be represented like this. So this is the case. Now let's understand about vector space in 2D. Vector space in 2D. So vector space in 2D. So for 2D, like we have already done this example, right? We have already done this example. This was the same example itself. Okay, like I want to show you visually what does this mean. So let's take a few examples. This has already been done over here. This can be written in row format or in column format, both are same. So this part, right, this whatever part I will talk for the next 10-15 minutes, this is just a theoretical part. Okay, so just whatever I'm saying to you, you just need to know that amount. No need to know very high amount of this, because this is anyways theoretical part, and if you understand the theoretical part, that is enough, because we have been doing the same thing already. Conceptual part, just few notations, few terminologies you have to understand. Okay, so here this v will be r square. Like I am taking one example of 2D vector. Okay, v will be r square equals to, let's say 2 1, then 1 2, then 1 comma 1. Okay, so you can write this in the column format also. Okay, whatever, like the why am I writing this in both formats, because so that you don't get confused with this, because gate can give you both formats, either in the row format or in the column format. So this can be 2 1, this can be 1 2, this can be 1 1. And this I can write like this. So this will like 2 1. 2 means 2 in the x direction and 1 in the y direction. So what does this mean visually, that I am trying to explain you. So this is 2 1, right? 2 in the x direction and 1 in the y direction. So this will be here, and 1 in the y direction, 1 is here, and 2 in the x direction. Like now with this 1 2 1 2 1 2 means 1 in the x direction, 2 in the y direction. Okay, now this 1 comma 1 1 1 1 means 1 in the x direction, 1 in the y direction. This will be somewhere around here. Okay, so let me color this differently, all of them. Okay, so this is about this. So now these are like set of 2D real vectors. These are set of 2D real vectors. So vector space in this case is known as set of 2D real vectors. That is the vector space in 2D. That is the definition of vector space in 2D. Okay, so this will like whatever set there will be, we will be able to cover this in 2D, like in this 2D plane, right? If for some reason I have a 3D line like xyz, then I won't be able to represent that, and that won't be a vector space in 2D. Okay, so let's understand the vector space in n dimension. This is the what do you say, proper definition of n vector space. So vector space in n dimensions means I have a v vector space which belongs to this r raised to power n. N means the dimensions. Okay, if I have n dimensions, basically 3 dimensions, 4 dimensions, like that, and r means all of them will be real. All of the each of the elements will be real over here, and it will be called a set of n dimensional real vectors. So this was about like just a basic about vector spaces. So here few definitions are given. You try to read this, and that is it. Basically, a vector space comprised of vectors collectively with the associative and commutative law of additions of vectors, and also associative and distributive process of multiplication of vectors by scalars is called vector space. Basically, vector spaces have to satisfy few axioms and conditions. So I will just skip this, and I will ideally tell you what are those conditions. But before going to those conditions, I want to tell you what is the difference between vector space and vectors. Okay, so you might get confused, sir, what is the difference? Like it is also vectors, right? So the difference is vector is a part of vector space, whereas vector space is a group of objects which is multiplied by scalars and combined by vector axioms. What are these axioms? I'll talk about, but vectors are part of vector space, right? So here this is a vector space. This V is a vector space, and each of these are vectors. So that is these are vectors, and vector space is a part of vector space because this is covering a space, right? Covering a space. That's why they are called as vector space. I'm covering the space, okay, with some linear combinations. What are those combinations we'll talk about? What are those axioms we'll talk about? So this is the first axiom. Axiom is about the condition of vector addition. So basically, you can go through this. There are a few laws that they have to satisfy. Basically, they are not that important for gate point of view, but just bit of theoretical knowledge you should have. That's why I'm teaching you all this. Okay, so commutative law for all vectors x and y v, then x plus y should be equals to y plus x. So if I have two vectors inside the vector space, then if I do x plus y, I should be same as y plus x. Those two should be same. Then they x and y are belonging to the same vector space. Now associative law. What is the associative law? For all vectors x, y and z in V, then x plus y plus z equals to x plus y plus z. Okay, like first you can add y plus z, then you can add x, or first you can add x plus y, then you can add z. It doesn't matter. Then identity element. Okay, additive identity. Basically, if you add 0 with it, you will get back that same vector itself. It won't change. Additive inverse. Each vector will have its additive inverse, that is minus x. It has to satisfy, right? And for scalar multiplication, now like c is a scalar number and x is any vector, okay, and d is also a scalar number. If I multiply d, then vector b, if I multiply d times v first, then multiply c, that should yield me the same result as multiplying c times d, then vector v. Okay, these are all rules. Distributive law also you can follow. We have two distributive law. One is for the scalars and one is for the two vectors. Okay, then we have unitary law. So unitary law is for all vectors x in v. Unitary law is for all vectors x in v. Then 1 dot v equals to v dot 1 equals to v. Okay, so this is what the unitary law is. Okay, so yeah, these are few examples of vector. So basically, let's do one example problem, and from there we'll understand how to add two vectors or how to write the minus v vector, right? So here we have two vectors u v, be the two vectors in r raised to power n dimension. In this case, it is not r raised to power n dimension, it is r raised to power 3 dimension, right? Because we have 3D vector. Thus form vectors u minus v and minus v. So basically, what will be my u minus v and minus v? So u minus v will be simply subtracting these two vectors, right? So u vector is 1 minus 1 1 and minus v vector is what? Minus 1 minus x and 1. Okay, and obviously they have also asked us to find the minus v, so minus v is this, and u minus v will be simply u plus minus v. So u plus minus v equals to simply 1 minus 1, this will be 0, minus 1 minus x, this will be x, 1 plus 1, this will be 2. Okay, so 0 minus x. So this is another answer to this question. This is just an example problem. Okay, just to give you a brief idea how we do the vector addition and subtraction, all those things, right? So this is what these axioms mean. Okay, so don't need to go too much in depth with this, don't take too much stress about this, all this, right? No, don't need to take stress, but whatever I have told you, right, at the starting, all these things you have to understand. Few standard vector spaces. What are standard vector spaces? These are the standard vector spaces, n dimensions and all real numbers. This is more important because in the question the language may come like this. We have a vector space of n dimensions, of 2 dimension, and of all real elements. So then you have to understand they are talking about this. It is a set of vectors which are 2 dimensions, okay, which can be represented in this 2D plane, and all of them are real numbers. Okay, so yeah, these I am telling you just to understand the language of the question, because they may play with the language of the question. That is why it is very important to understand all this. Now let's go to the next topic, that is the vector subspace. So what is vector subspace basically? So a vector subspace is a vector space that is contained within another vector space. So every subspace is a vector space in its own right, but it is also defined relative to some other larger vector space. So what do I mean by this? So here, what is the vector space? So here, right, let me take this example. This means all the this all 2-dimensional, right? This whole 2-dimensional space is my vector space. This whole 2-dimensional space is my vector space. Now I only want the first quadrant. I don't want all this. Okay, I don't want all this. I only want the first quadrant. Then what should be my condition? Okay, I want only a first quadrant. So at the first quadrant, what are the conditions for x and y? X and y both are positive in the first quadrant. So I will say, please give me a vector space of 2D real vectors whose x and y component are all positive. Okay, x and y component are all positive. That will be a subspace of this vector, right? Vector space in 2D. That will be subspace of vector space in 2D. Okay, a vector space in 2D is denoted by v, and x is another vector that is also a vector space in 2D, but with a added condition that my x and y component should be all positive. That means it will be a vector subspace. It will be vector subspace of v vector subspace. So it is also subspace. It is also a vector space, but it is a vector subspace because I am not covering the whole of this 2D plane, I'm only covering the first quadrant. Okay, so that is what this subspace means. It is also a vector space, but it is a vector space of but it consists a smaller portion of a larger vector space, right? So I am only covering the first quadrant instead of this whole 2D plane. That's why it is called a subspace. But a subspace is also a vector space. Okay, so V is a vector space, W is also a vector space. But if I write like this, so this is a symbol of subspace, right? Symbol of subspace, then W belongs to V, then W is a subspace of V. Okay, W is a subspace of V. So this is what this vector space means. Yeah, sorry for the interruption. I was just checking whether it was recording or not. So let's go back to this question. So this is the next question. So this question is telling that let V be a 3D vector space. V is a 3D vector space. Basically, it is a set of 3-dimensional vectors which satisfy the following equation: x, y, z equals to 1. So x, y, z equals to 1 is satisfying, right? Hence, I can write this as a subspace. So W will be my subspace of V, which will satisfy x, y, z equals to 1 and also a 3D set of 3D vectors. Okay, so x, y, z are this, and x, y and z all belong to real numbers. So which of the following can represent W? Which of the following can represent W, right? Which of the following can represent W? Which of the following is true? Basically, if V is equals to 1 minus 1 minus 1, right? If V is equals to 1 minus 1 minus 1 and like 1 by 2 2. So this is sorry, I should write this all as W, not V. Actually, my fault. All of these are W. So basically all of these are V, right? All of these are V. This is correct because this is set of 3D vectors. Okay, but which of these are W? Which of these are W? Because V will be larger subset because all of them are V, but are all of them W? Let's see. So they have to satisfy this condition, right? X, y, z equals to 1. So I have to multiply the x component, y component, and z component, and all of multiplication of all of these three will yield me 1. Okay, so 1 times minus 1 times minus 1 is 1. Satisfying. First vector is satisfying. The next vector. Now, first of all, obviously, all of these are 3D vectors, right? And all of them are real. So we don't have to check those again. So we will just check this condition. Now let's come to the second vector. 1 times 1 by 2 times 2. So this is also 1. So this is correct only. This is correct only. Now let's come to this. W equals to 3 times 1 times 1 by 3. Again, this is 1, correct. 1 times 1 times 1. Again, this is correct, 1. Now, W equals to 0.5 times 2 times 1. So this is also 1. Then 1 times minus 1. This is also minus 1. So again, this is not correct, right? This is satisfying 1, but this is minus 1. So this is not satisfying. X, y, z should be equals to 1, not minus 1. So this is not satisfying. So this is wrong. Now, what about this one? 2 times 3 is 6. 6 times 1 by 6 is 1. Then 1 times 1 times 1 is 1. So this is also correct, right? So A, B and D will be correct. W won't be correct. But W is V, right? I mean, sorry, not W. This is V, right? So this is a 3D vector subspace. This is correct. But this, right? Basically, the thing is, they won't satisfy, like this won't satisfy this condition. Hence it is not the vector subspace. So W is not like this is not equal to W, but this is equals to V. Okay, as we can observe that V is a larger set of vectors and W is a smaller set of vectors. That's why it is called a subspace. I hope you got the point what I am trying to explain over here, right? So basically, what are a few notations over here? So you can see, like if I write like this, so that V is a 3D set of vectors, okay, where all real set of vectors where x equals to 2y. So how can I write this? I can write that I can assume that y is equals to alpha 1, then my x will be equals to 2 alpha 1. Okay, y will be equals to alpha 1, x will be equals to alpha 1. Okay, so this is what my x equals to 2y is. Now you can write the same thing. Y is for another vector, right? You can write the same thing, alpha 2 and 2 alpha 2. Okay, so this is how you define a vector subspace. This is the basic notation of a vector subspace. Okay, previously I was giving you the notation for a vector space. Now I give you the notation for a vector subspace. They have to satisfy few particular conditions, right? So yeah, let's basically now do this question. Let's basically do this question. Here we have this V1, which is also a vector subspace of all 2D real vectors which has to satisfy this particular condition x plus y equals to 0. And V2 is a simple set of vectors. It is a simple vector space of 1 minus 1 minus 1 1. Okay. Now V1 is a vector subspace of V belongs to all 2D real vectors. Is this correct? V1 is a vector subspace of all 2D real vectors. 2D set of all 2D real vectors. Is it correct? So this is correct because V1 is already V1 is this. Also it has to satisfy this condition. So it is a smaller set of R square. Okay, smaller set of R square, and that is fine. That is fine. So V1 is a vector subspace, which is correct. V1 is a vector subspace. Why? Because what does this R square mean? R square means that x and y, I will cover the whole 2D plane, right? I will cover the whole 2D plane. Now x plus y greater than equals to 0. X plus y equals to 0 means y has to be equals to minus x. So it will be something like this. So my vectors will only lie in this line, but that was my whole vector, right? R square was my whole vector, and obviously this line is already included in this whole vector space. So this line, right, will be a vector subspace of this R square. You can understand visually, or if you want to understand just by theoretically, right? Just theoretically you can understand this R square and this also R square, and this has to satisfy that extra condition as well. So it will obviously be a subspace. Okay, it will obviously be a subspace. This one is correct. Now let's come to the second, V2. V2 is a vector subspace of V1. So V2 is 1 minus 1 and minus 1 1, and it is talking that it will be a vector subspace of V1. So let's do this. So V2 is 1 minus 1. It is all like this is two-dimensional set of two-dimensional vectors, and these are all real. And if I do x plus y, this will be 0. If I do x plus y over here, this will be 0. Okay, so 0 0. So now basically now what will happen is this a subspace? So are there any other vectors that I can represent also? Yes, I can represent what, 2 minus 2, then I can represent minus 3 3, this is plus actually, then I can represent minus 4 4, all of this, right? I can represent all of this. I can represent all of this, right? All of this. So yeah, basically that is the case. So yeah, this is a vector subspace because it is satisfying all the conditions. Okay, satisfying all the conditions, but obviously not all the elements are present over here. There will be unlimited number of elements because it is just line, right? It is a line and it never ends. So satisfies all the condition. So this is also correct. Okay, I hope from these two statements you got the idea about vector subspace. Like how can I write this? So like notation wise, how can I write this? So here my V basically belongs to R square, so which is x y z. Okay, and x, it can go to infinity, right? It can go to infinity. There are more x1 y1 z1, and it can go to infinity. And x comma y comma z all belong to real elements, right? This is what this first definition was. I'm just trying to do this formally. So, and what is V1? V1 is also R square, but it is satisfying particular equation x plus y equals to 0, right? So obviously I can write that V1 will be a subspace, vector subspace of V2, not V2, so V. Okay, this is the thing. Now also I can write that V2 is this, right? V2 is this, and V1 is already that, we know, and obviously these are satisfying. So I can write V1 is subspace of V2. V1 is subspace of V2. Okay, this is how we formally write this. No, sorry, not v1. v2 is a subspace of v1. v2 v2 is subspace of v1. Okay, this is how we formally write this, right? So this is about the subspace. Now we'll start with the linear span. Okay, so what is a linear span basically? So I will try to explain you all these things. So slowly you will be able to understand these things bit by bit. So don't worry if you are not able to grasp this initially. When we'll do more example problems and when I will explain you more throughout this lecture, you will be able to grasp the linear span. So generally it is a bit difficult to grasp it the first time around. So you can rewatch this again. So let's first read the definition. The span of a set, or also known as linear span, this is also known as linear span. The span of a set of vectors, also called linear span, is the linear space formed by all the vectors that can be written as a linear combination of the vectors belonging to the given set. So this linear span is basically also a vector space itself. It is also a vector space, but what is the special thing about this is it can be written as a linear combination of all the vectors belonging to the given set. So let's say I have a vector set over here, right? Vector space over here. Like this is a set of vectors, right? This is a set of vectors. I can write this linear span of these vectors. How? This will include all the linear combinations of this set of vectors, of all the vectors in this, right? Of all the vectors inside this. So this is denoted like this. This is not a single element. This is not a single element. There are multiple elements over here. So span of X is written like this. It is also a set of vectors, but it is a set of linear combination of vectors, linear combination of the vectors. So it is a set of linear combination of all the vectors present in vector space X, where alpha I is basically scalar because we are doing the linear combination, and power will be 1 over here, and xi will be all the vectors, individual vectors, and I can go from 1 to n. What is n? N is basically the number of vectors present over here, right? Number of vectors present over here. We can do that many linear combination. Okay, so let's try to understand with the example. So what do you mean by linear combination? So this is a linear combination, right? This is a linear combination. All the summation of the vectors will be span of this vector space. If I have vector space like this, now this is also a linear combination. Now we have more as well. We will have more as well here, right? We'll have more linear combinations, right? We'll have more linear combinations. Okay, not just this. Okay, so it will be set of all the linear combinations, right? All the it will be by all the vectors that can be written as a linear combination of the vectors belonging to the vectors given set. Okay, so let's do example over here. So here Lx is a linear span of X where it consists a set of vectors. These are two set of vectors where these are linear combinations of the vector space X. You can see, right? This is a linear combination, right? Summation of all the vectors, linear combination. Then x1 plus 2 x2 minus 3 x2. This is also a linear combination, right? So basically it is a linear combination, span. Now what does span mean? Span means it is a set of vectors. It is basically covering this whole space. Let's say if my n was 2 in this case, okay, 2D vector, so it will span this whole 2 dimension. Okay, with a linear combination of 2 vectors I can span this whole 2 dimension, but it depends if those two are linearly independent or not. That will explain. So let's say for example my vector is 2D, right? My vector is 2D, okay, 2-dimensional real space, and it has 0 1 and 1 0. Okay, 2D 0 1 and 1 0. Now are these independent? These are linearly independent, we know, right? Determinant is 0. All this we know. We have already studied this concept, but again we'll use this concept just in a few seconds. Don't worry, because we are just repeating the same thing. We're just mainly focusing on the linear dependency and independency. So these two vectors are linear independent. So one vector is here, this is I cap, okay, 1 comma 0, and another vector is here, this is j cap 0 comma 1. Now basically the case is, with the help of these two vectors can I represent this whole 2D plane? Yes. So these two vectors are spanning this whole 2D plane. Okay, these two vectors are spanning the 2-dimensional real space. 2-dimensional real space. So that's why I call these two vectors as the linear span of this 2-dimensional real space. Okay, not these two vectors, sorry, not these two vectors, the combination of these two vectors. The combination of these two vectors will slowly solve, and from there we'll understand. So let's first get cleared, accustomed with the few terminologies of this linear span and vector space. So if someone says to you vector space X spans vector space V, what does this mean? It means that X is spanning V, right? X is spanning V. Or if they say to you that vector space V is spanned by vector space X. So V is spanned by X. So X is again spanning V. So X is again spanning V. So these two are same only. So basically what does this mean? This means that I can write like X is spanning V, right? X is spanning V. That means X I can write as linear combinations, and that will be equals to my first vector V1. So V is what? V is the linear span. So V1 first vector I can write as this xm, x2, V2 I can write beta 1, beta 2. These are all linear combination of X vector. So here X is this, right? And Lx is this. This is the Lx, because I'm able to write the linear combination. Okay, so this is the span. This is the Lx. This is the Lx. Okay, so these are M vectors, right? These are M vectors. Fine. So like you can see, right? So I can write linear combinations of all of these vectors and then add them up, and I can write n vectors. Okay, and it doesn't matter, here I have n vectors, right? And here I have m vectors. So it's okay if I have n vectors and m like what do you mean by this? If I have only, like let's say I have total in this set, right? I have total three vectors in this set. Now I can write only one vector also, linear span. That is fine, because that will be linear span also, because linear span means basically it is a set of vectors of linear combination of this vector space. It's okay if it has 1, 2, it doesn't matter, right? So that is the thing. Now this was the first case I wanted to explain it to you. Now like I can write V is a linear combination of all vectors of X. So what I can write, that Lx means, or here V, what does V represent? What does V represent over here? Let me just represent that. V, basically we can write linear combination of all vectors of X. Okay, V is a linear combination of all vectors of X. So let's now basically understand few terminologies. So let V equals to V1, V2, Vn, right? And X equals to X1, X2, Xm. Okay, so if they're talking that X is spanned by V, X is spanned by V, or V spans X, what does this mean? So here V is spanned by X, right? V is spanned by X. That means X I can write as linear combination. V I can write as linear combination of X. That is what this means, right? V is spanned by X. So X is spanning me, right? X is spanning me. So basically I can write all the linear combination of X, and then that will be equals to V. So this is what this means. So X is spanned by V, right? So if X is spanned by V, that means now the cases are reversed now. So X is spanned by V. That means I can write all the linear combinations of V, V1, V2, V3, right? Then I will be able to represent X, X2, X1, Xm, it doesn't matter, right? So this is what this means. Or V spans X. So all the linear combination of V I am taking. So that is what spanning means. And then I'm writing it in X, right? In terms of X. Okay. So this is what this means. Next is V is spanned by X, or X spans V. Now V is spanned by X. So V is spanned by X. So V is at the starting and is spanned by X. So I am spanning throughout X. Okay, writing all the linear combinations of X, and then I'm writing it in terms of V. Okay, that is what this means. Or X spans V. If X is spanning V, that means I'm writing all the linear combination of X and writing in terms of V. Good. Okay, here V spans X. So I'm writing all the linear combination of V and writing in terms of X. X is spanned by V. X is spanned. So I'm spanning X again and writing in terms of linear combination of V. So I have got this point. Now this third point is third case is very critical. So here x belongs to linear span of B. What does this mean? What does this mean? X belongs to linear span of V. Now what does this linear span of V means? Linear span of V, what does this mean? I can write this V like linear span of V. What does this mean? So I can write this V as alpha 1 V1 plus alpha 2 V2 right? This is what this linear span of V means. Okay, so I'm spanning throughout the V vector. Now x belongs to this linear span. Okay, linear span. So x is equals to this. X is equals to this. X belongs to this. So I can write basically this statement, right? This first statement that x is spanned by V. In this case, this will be same as this. That x is spanned by V. Let me do one thing, that take this to the next page, else we won't be able to cover this one up. So here this means that x is spanned by V. X belongs to linear span, right? X belongs to linear span of V. So I'm writing all the different linear combination of V, and I can write x in terms of V. X is spanned by V. Okay. This will be this. Oh, which color should I choose? I'm just literally confused. Yeah, let's choose this or not this. This has also changed. Then the fourth case, right? What is the fourth case? So the fourth case is basically V belongs to linear span of X. So what is the linear span of X? What is the linear span of X? This means basically the linear combination of X, right? Again, alpha 1 x1 plus alpha 2 x2 and right? So V belongs to this. So V is equals to this. So V is spanned by X. V is spanned by X. Why am I showing too much emphasis in this terminology? Because in the gate question this may be asked, right? These types of terminology terms may be used, and if these types of terms are used, then you will be confused. So you have to be really careful about this. So V is spanned by X. So we'll just change the color of this. So I will just copy this case to over here. Okay. Okay, so these are the few terms you have to take care of, because in the question they may give you terms like this, that X belongs to linear span of V. What does this means? What is linear span of V? Linear span of V is the linear combination. You can remember it like this. Linear span of V is the linear combination. Now X belongs to the linear combination. So X is equals to this. I will write X is equals to this. That means X is what? X is spanned by V. X is spanned by V, or X is the linear span of V. Okay. This also you can understand the same analogy. So let's do few examples. So here let v1, v2, v3 are these three vectors, and x is vector of real three-dimensional space. X is a vector space of real three-dimensional space. Now, does vector v spans vector x? Does vector v spans vector x? We have to understand this. How do we understand this? So basically, what does this mean? This means with a linear combination of these three vectors, can I be able to reproduce my x vector? Will I be able to reproduce it? So what does this means? What does this statement means? meaning of this statement. Okay, so what does this means? That means that with linear combination of x, will I be just hold on a second, let me check if everything is recording right. Yeah, this is recording. Will I be able to produce my vector x? Will I be able to produce, not my vectors, my vector space v, right? Okay, so this is what this means. So basically, what is my x? If I write my x, so I can write my x as, not my x, sorry, hold on a second. Okay, yeah, so my I can write my x as like this, right? X is set of all 3D vectors. So it is set of all 3D vectors. This will be like 1 0 0, then 1 minus 1 1, then 2 3 1, whatever the numbers are here, right? So this is a set of all 3D vectors, right? Set of all 3D vectors. So here set of all 3D vectors. Okay, so how can I write this linear combination? So there are two methods to find out whether this V spans vector x or not. So how do we find it? So first method is the basic method. Okay, first method is the basic method, and we'll go with the fundamentals. So I have this V vector, right? V vector is a set of vector v1, v2 and v3. Okay, then V spans x. Okay, V spans x. We have to find out V spans x. How do we find out? So we have to use the linear combination, right? Linear combination of v1, v2 and v3. So we have to use the linear combination v1, v2 and v3. So basically, how can I write this? So basically, what is this? This is what? This x I can write. This x I can write like this, right? X, y, z. This x I can write x, y, z. Okay. This is what this x means. So I have to find this x, y, z now. So basically, with a linear combination of this v1, v2, v3, I will be able to find x, y, z, and where x, y, and z are all real, right? X, y, and z are all real. X, y, z are all real. Okay. So basically, what are the linear combination of v1, v2, v3? So alpha 1 v1 plus alpha 2 v3 plus alpha 3 v3 should be equals to this x, right? Should be equals to this x. What is this x? X is x, y, z. So alpha 1, what is v1? v1 is 1 minus 1 0, 1 minus 1 0. What is alpha 2? Alpha 2 is 201. Alpha 2 is 201 plus alpha 3. Alpha 3 is 124. Alpha 3 is 124 equals to what? Equals to x, y, z. X is x, y, z. Okay. So with the help of these combinations, right? Alpha 1, alpha 2, alpha 3 are all like any real number. Alpha 1, alpha 3, alpha 2 are any real number. So alpha 1, alpha 2, alpha 3, any real number, but obviously not 0. Okay, they can become with 0 as well. Okay. They can be 0 as well. So basically these has to be satisfied, right? These condition has to be satisfied, then we can say that it is spanning, because for all, I have to say, for all x, y, z, above condition needs to be satisfied. Above condition needs to be satisfied. I will write this in small. For all x, y, z, above condition needs to be satisfied. Okay, so basically this is like a system of equations now. So let us convert this into system of equations. So I will first equate the first row, second row, and third row. So again we're coming back to that same concept again, system of equations. So that is very important. We're just learning the same thing over and again, just in a different way. Alpha 1 plus 2 alpha 2 plus 2 alpha 2 plus alpha 3 plus alpha 3 equals to x, equals to x. Then minus alpha 1, then 0 plus 2 alpha 3 equals to y, then 0, then alpha 2 plus 4 alpha 3 equals to z. Okay, equals to z. So this is what, this is like a system of equations. This is like a system of equation where x, y, and z on the right hand side can take any value. Okay, basically this is homogeneous and non-homogeneous both, right? System of equations where the right hand side is varying in our case. X is real, y belongs to real, and z belongs to real, right? Z belongs to 0, real. So basically what needs to happen? What needs to happen here? We need to find a solution for alpha 2, alpha 3, alpha 4. Oh, sorry, alpha 1, alpha 2, alpha 3. Right? We need to find a solution for alpha 1, alpha 2, alpha 3. So basically, this system of equations need to be consistent. They need to be consistent. Need to be consistent for us to get a proper solution. It doesn't matter if we get infinite solution or trivial solution. Not trivial, sorry, infinite solution or unique solution. Okay, because this is non-homogeneous as well. So it doesn't matter. But they need to be consistent. So if they need to be consistent, what does that mean? That means, let me write it over here. This is 0 times alpha 2. Okay, this is right hand side. This is 0 times. Now basically, what is this, right? We already know this. This is A matrix. This is A matrix. And what is this? This is a B matrix, right? This is B matrix. So basically, if a system of equations has to be consistent, that means my augmented matrix rank of AB has to be equals to rank of A. Okay, rank of AB has to be equals to rank of A. Right, rank of AB has to be equals to rank of A. So this has to follow. It doesn't matter whether this is like less than 3 or is equals to 3. If it is equals to 3, then we'll get unique solution. If it is not equals to 3, less than 3, we'll get infinitely many solution. It doesn't matter. Okay, it doesn't matter for how many values of alpha. Just what matters is this has to be equal, because I need a proper solution. If I get a proper solution, then only I will be able to say yes, this equation is satisfying. Now if this equation is satisfying, this condition is satisfying. Now if this condition is satisfying, that means it is a linear combination, like X is a linear combination of v1, v2, v3 for all alpha 1, alpha 2, alpha 3. That means this question, whatever it has asked, does vector v spans vector X with linear combination of X, this will be satisfying, right? This will be true. This will be true, right? We will be able to produce all these things. So v will span X then. Okay. So basically we have to find the rank of this. We are again coming back to the same concept of rank. Okay. So everything comes back to rank itself. So let me write this in the matrix format now. A, B. Okay. So this will be 1, 2, 1, minus 1, this is 0, this is 2, this is 2, 0. Okay, where did I go? 0, 1 and 4, right? Okay, this is also plus over here. Okay, so 0, 1 and 4, and my B matrix is this, right? XYZ. So B XYZ can be anything, right? XYZ is varying this time. That is why this is difficult to calculate the rank. Anyways, we're not that interested to the rank. We are mainly interested that the rank of AB should be equal to rank of A. We're not exactly interested in the final answer. It doesn't matter to us. So obviously, for finding the rank, we have to convert this into the row echelon format. So we have to convert this into the row echelon format. So basically, what I'll do, I will convert this into row echelon format and then again come back. Okay, I have converted this in the row echelon format. So first, what I did, I just added these two rows, right? Row 1, row 2. So I got a 0 over here. Then I wanted to make a 0 over here. Then what I did is I subtracted row 3. I subtracted from row 3, row 2 by 2. Okay, so I got this 0 over here, right? So if I subtract, this is 1.5 minus 4 minus 1.5. So this is 2.5. So this will be 5 by 2, right? So this will be z minus x by 2 and x plus y. Now what was our condition basically? So our condition was to make this rank of A be equals to rank of A. Okay, so for all values of x, y and z, for all values of x, y and z, I should write for all x, y and z. Okay, so this is for all values of x, y and z. So now basically how to make this happen. So here what do I see? I see the rank of A is always 3. Rank of A is always 3. It cannot go to 0 because number of 0 rows in A matrix 0, right? So rank of A will be always 3. Rank of A will be always 3. Now if rank of A is 3, then rank of AB will always be 3. It doesn't matter if this is 0 or non-zero, if these are 0 or non-zero, rank of AB will also be always 3. So which will be equals to 3. Okay, hence for all values of x, y and z, for all values of x, y and z, okay, for all values of x, y and z, and basically what is for all values of x, y, z, hence we can say that this is a linear span. This is a linear span of V, right? So from here we can say this condition is satisfying. This condition is satisfying. That means that this statement is correct. This statement is correct that vector V spans x, or basically our x is basically linear span of V. X is linear span of V. So I can write x is a linear span of V. Okay, so this is how you solve this from the basics. Okay, this is the method 1. This is how you solve from the basics, right? So V spans means V is a linear combination. V linear combination is equals to x, right? That's why x is a linear span of V. So with the linear combination of V, I can write x, right? So that is what this statement is, right? So V spans vector x, here if you go to the first case, like v is spanned by x, or like you can say v spans x, that is I can write x in terms of linear combination of v. That is basically what I'm trying to say over here, right? So yeah, sorry, the light actually just went off. So I will just try to do one thing, completely wrap up this lecture. So basically this is one thing, okay. And the method 2, what I was thinking was I will skip this method 2 because you only use this method, okay. At first glance this may seem very time consuming, but obviously you don't have to do it all this, right? I just have to explain on this to you, so that's why I have written all this. Simply you just directly write this augmented matrix, and from there you can find the rank, okay. You just use this method. Method 2 is same, only just bit twisted. They are using the same concept, that's why I'm skipping the method 2 now. I'm giving you a few homeworks, and the next lecture I will restart again. So these are a few examples. Just take a screenshot and solve this question. Then again, this is also another question. Take a screenshot and solve this question using the same method. This also you have to take a screenshot and solve this question, right? So I think that's it. End of this lecture. In the next lecture, I will try to quickly give you a recap of whatever we learned in this lecture, and in the next lecture, that will be the end of the linear algebra chapter. I hope you learned a lot from this. Okay, so I'll see you in the next video.